Hey there. We've been working with solving equations in chapter 1 so far and some things related to that. What we're going to do now is we're going to change our focus and we're going to be working on solving linear inequalities. The goal for this video is that you will solve linear inequalities and you will graph their solutions on a real number line. Now this is something you've seen in Algebra 1 before, so it's really a review. Let's go through some key things that you need to understand before we even talk about solving linear inequalities. Now, the beginning of things that we need to talk about are solutions of linear inequalities, because whenever you're trying to talk about the solution of an inequality, it's going to be different, in a sense, than what the solution of an equation would be. For instance, just looking at a basic equation, you know that the only value of x that I could use that could make this equation true would be 6, correct? You're used to seeing equations where there's one solution. You'll see in the next section of this chapter equations that have two solutions, all right, or no solutions, that kind of thing. But nevertheless, you have a finite number of solutions with equations typically. Okay, now that's not the case with inequalities. In fact, with inequalities, if you have any solutions at all, you have an infinite number of solutions. Now, I want to go through some examples of what I mean by that. Okay, now, just like with equations, a solution of an inequality is going to be any number you can substitute in place of the variable, any number that you can substitute in place of the variable that would make that inequality true, all right? And so the inequality x is less than or equal to 10. Well, there's not just one answer to that. You can't just say 9 is a solution, or 7 is a solution, or 2.14 is a solution. There's an infinite number of solutions. And because there's an infinite number of solutions, often whenever we're trying to discuss the solutions to an inequality, it's better to do so by illustrating those solutions on a number line. So in a lot of the problems that you're going to be doing involving inequalities, you're not only going to be told to solve the inequality, but you're going to be told to graph the solution on a number line. And I'm going to remind you of how to do that. Of course, with this example right here, it'll be fairly straightforward and you already understand it. I will show it to you. I'm also going to show you two others. I'm going to go ahead and put those on the screen right now because I want you to get used to seeing the solutions of compound inequalities as well, although it'll be in the next video before I discuss actually solving compound inequalities. And I'll describe what I mean by compound here in a moment. But I'll show you in these three examples how you display solutions for an inequality on a number line. And for part of that process, I just want to explain to you, whenever you draw a number line, how you choose what numbers are a part of your number line, because you don't always have to just put 0 in the middle and then 1, 2, 3, 4, 5. In fact, that's not useful most of the time, unless you just happen to be working with simple numbers. You can put 0 anywhere you want to on the number line. Let's just say you put 0 right there, although I would prefer that you always at least show where 0 is on the number line. Okay, that's 95% of the time anyway. And then what you can do is you can choose your intervals to be whatever you want them to be. You don't have to go by ones, you can go by twos, and that's what I'm going to do here. In fact, I'm going by twos, but just to keep it a little neater, I'm only labeling every other interval. So that's 0, 2, 4. All right, now the rest is common sense, so there's no reason for me to really explain beyond that as far as the intervals go. So I've chosen my intervals, and then the next thing I've got to do is actually graph the solutions. All right, now we're trying to show that the solutions are any number that is less than or equal to 10. So my solutions begin at the number 10, and then they'll include anything less than that. Now you might remember, whenever you're looking at your boundary number for the solutions of any inequality, that sometimes you graph an open circle and sometimes you graph a closed circle at that boundary number, depending on whether this is an equals or whether that boundary number is included in the solutions or not. And 10 is included because our solutions are allowed to be equal to 10. So what we're going to do is we're going to put in a filled-in circle at 10. Now notice how I labeled the number that this dot represents. I prefer for you to do that if it's not already labeled by the intervals that you chose. All right, and then we want to show that every number less than 10, which would be on the left side, is also a solution to this inequality. So we'll just draw a little line, or we'll highlight, however you choose to do it. In fact, for me, highlighting will probably be the easiest. So I'm going to go ahead and highlight everything that's less than 10. including the arrow at the end just to show that the solutions keep on going beyond what you see on the number line. So there's graphing the solutions for a linear inequality. All right. Now, in the next example, you can see that I've got a compound inequality, which one way of describing that is you see that I've got two inequality symbols here. This is what would be called an AND inequality. We'll get into that in the next video. But essentially, this is telling me that the solutions are anything between -2 and 5, including 5, but not including -2. All right, so here's how that graph is going to look. We're going to go ahead and decide on our intervals, and then we're going to graph our boundary numbers first. And you can see where I put 0, and you can tell that I was going by ones this time. And all right, there's the boundary numbers graphed. This one with an open circle because -2 is not included in the solution set, and this one with a filled-in circle because 5 is included with the solution set. And then we're going to go ahead and highlight everything between. Great. And then one more type of compound inequality that you'll see is what we call an OR inequality. Now, with an OR inequality, the solution can be anything that makes the first inequality true or the second inequality true. It doesn't have to be the numbers that make both of them true. It's the numbers that make either one of them true. And we have to highlight all the numbers that make either one of them true. Now, we still begin by graphing the boundary numbers and choosing our intervals. And just notice I didn't put the 0 in the same place in this case because the key numbers I was trying to show, 0 and -5, it fit a little bit better if I put 0 closer to the right and the -5 closer to the left. All right, use your judgment when you're choosing your intervals and where the 0 goes on the number line and so forth. All right, now I said we're going to shade every number that makes either one of these inequalities true because of that word OR. So we want to shade any number that's less than -5. Well, here's the -5. And the numbers that are less than -5 are, of course, to its left. So that's anything that makes this first inequality true. And then we're going to shade anything that makes the second inequality true. Now 0 is already shaded. And then we'll just go ahead and highlight the rest of the number line to the right because that's where the numbers greater than or equal to 0 are going to be located. So that's how you show the solutions of inequalities, and that's kind of what the solutions are. Any number that makes the inequality true is going to be a solution, and you have an infinite number of solutions. Even right here, you might think there's a limited number of solutions because you might just think, well, -1, 0, 1, 2, 3, and 4, and 5 are solutions. But keep in mind that 0 might be a solution, but also 0.1, 0.2, 0.3, 0.35. There's an infinite number of solutions there. That's my point. Now, I've got one more key concept to remind you of that you're pretty familiar with, I believe, before we can actually go on to solving inequalities, and that's that I want to remind you of how the multiplication and the division properties of inequalities work, because they work a little bit differently than with equations. All right, now what do I mean by those? Well, the multiplication property of an equation is where if you multiply one side of the equation by something, you got to multiply the other side by the same thing. All right, you're multiplying both sides by the exact same number. And that's the same thing that's true with inequalities. Now, let's go ahead and look at this then. Let's look at the inequality A is greater than B. And let's suppose that we have some real number C that is greater than 0. In other words, we've got a positive number C. And then suppose I want to multiply the numbers A and B in this inequality by that positive number C. All right, well, first of all, if you multiply the left side by a number, you have to multiply the right side by the number. But the point is this: if A was greater than B in the first place, and you multiplied both sides of the inequality by a positive number, then the product A times C is still going to be greater than the product B times C. And very similarly, if I was going to divide that number A by that positive number C, that quotient would still be greater than B divided by that same positive number C. Okay? Now, here's where I'm going with this, and this is what you probably remember as a rule. There are instances when you're solving inequalities where you've got to reverse the inequality symbol, and I hope you remember that being whenever you multiply both sides of the inequality by a negative number or when you divide both sides by a negative number. And you'll see that in examples, but here's the property kind of written out. Let's take that same inequality, A is greater than B, but this time let's say there's a real number C that is negative. It's less than 0. Well, if I was to multiply both sides, both of those numbers a and b, by that negative number c, the inequality symbol is going to reverse. A times c would not be greater than b times c. Still, it would actually be less than b times c. Now, a quick example of that. I think you can agree with this inequality right here. I think you can agree that 10 is bigger than 5, can't you? Now, let's just say we take some negative number, like this is going to be my A, this is my B. Let's say I take a negative number for C, say negative 2, and I multiply both sides by negative 2. Well, if I multiply 10 by negative 2, that would become negative 20. If I multiply 5 times negative 2, that would be negative 10. It would be incorrect to say that negative 20 is greater than negative 10, wouldn't it? It just happened that whenever we multiplied both sides by the negative number, the side of the inequality that had the greater value ended up being the opposite side from where it first was. Whenever you multiply both sides of an inequality by a negative number, you've always got to reverse the inequality symbol in order for the relationship to be true still. All right, there you go. And similarly then, if you have that same thing where you got a is greater than b and you divide both sides by a negative number c, then the inequality symbol reverses as well. You see where it's greater than, divided by a negative number, both sides, and so the inequality symbol reversed. Very important to think about whenever you're solving inequalities. Well, now that we've talked about all the basic information that you need to know in order to solve inequalities, let's go ahead and solve some inequalities. We've got two just straight up inequalities to solve, and then we're going to work with a word problem involving inequalities as well. All right, so it says solve the inequality, then graph the solution. The rules for solving inequalities are the same as they are for solving equations. I would still like you to go through that SI process where you simplify the expressions on either side of the inequality symbol, and then you isolate the variable. All right, so here, hopefully you've already copied down the inequality. We're not going to bother with simplifying just because we can't simplify either side. 5x minus 11 you can't do because they're not like terms. Same thing with 2x plus 6. So we'll go ahead and begin by isolating the variable. Now, it's going to work the same way as it did with equations here. For instance, I want to cancel out the 2x from the right side of the inequality. Well, I've got to subtract 2x to cancel out that entire term and to make it 0x's. So let me subtract 2x from both sides. 5x minus 2x is going to be 3x. All right, so that's what you'd be left with. And then let's add 11 to both sides to cancel out the minus 11, and you get 3x is less than 17. And then we're going to use the division property, but we're going to divide both sides by a positive value. We're dividing both sides of the inequality by positive 3 here, so the inequality symbol will not reverse. We'll get x is less than 17/3. And most of the time when the answer comes out to a fraction, I say leave it as an improper fraction, although when you're graphing, it's often helpful to make that into a mixed number. You know 3 goes into 17 5 times with 2 left over, so 5 2/3 is what x has to be less than. And then we'll simply graph that on the number line. Now we already talked about choosing intervals, but notice where I graphed 5 2/3. If this is 4 and this is 6, this is 5, and then 5 2/3 would be closer to 6 actually than it would be to 5, so I just put it so it was closer to 6 than it was to 5. You don't have to get that exactly in place. And I made it an open circle because the boundary number was not included in the solution set. And then we'll go ahead and highlight the rest of the solutions, which will be to the left of our boundary number because we're looking for things that are less than 5 2/3, like so. All right, so same idea as it was with solving equations. All right, let's take a look at another inequality then. And this one you can see there is some simplifying to be done on the left side of the inequality. We need to go ahead and use the distributive property here first and get 24 minus 8x, and then we'll just copy the rest of it down the same way. Nothing we could do to simplify the right side of the inequality, so we'll just keep it or leave it alone as well. All right, and then we still got some light terms to combine on the left side of the inequality here, so let's go and combine those. So we'll get 24 minus 10x is less than or equal to 40 minus 6x. All right, now one thing I prefer with inequalities that I don't really care about with equations is I prefer to keep my variables on the left side of the inequality. That's not a big deal, but if we'll keep them on the left side here, it'll help me illustrate something else to you as well. We're going to isolate the variable now, so we need to combine all our variable terms on the same side, and I'm going to cancel out the x's from the right side so that I can have them all on the left side. And I'll do that by adding 6x to both sides. So negative 10x plus 6x is going to be 4x, or negative 4x actually. So we'll have 24 minus 4x is less than or equal to 40 after we add 6x to both sides. And then we'll cancel out the 24 by subtracting 24 from both sides, of course. So that'll leave us with negative 4x is less than or equal to 16. Now the thing that I wanted to illustrate here is that we're at the point where we're going to use the division property of inequalities here. We're going to have to divide both sides by a negative number though. And remember, when you divide both sides or multiply both sides of an inequality by a negative number, you reverse the inequality symbol. All right. Well, then negative 4x divided by negative 4 is positive x. And 16 divided by negative 4 is negative 4. So there's our solution set. Let's go ahead and graph it. And there we go. We highlighted all the numbers greater than or equal to negative 4, including negative 4 itself, right? That's solving inequalities. Now for a word problem. Well, let's go ahead and read it. I think you'll understand why an inequality is going to be necessary here. Says that you have $25 to spend on bowling, and you must spend $3.25 on shoes. Each game costs $2.75. Wants you to write and solve an inequality. Doesn't say anything about graphing, but write and solve an inequality to describe the possible number of games you can bowl. All right, so one instance where an inequality is applicable is whenever you have a budget, for instance, and you're trying to figure out how many times can you do something, essentially. So let's work on this. I'm going to make a verbal model to begin, just like I did in the video I showed you about problem solving. And let's think about what that verbal model needs to include. There's a few quantities described here. There's the amount of money that you have to spend. So let's just assume you don't have any more in your wallet than that. You don't have a credit card or anything. You can't go beyond $25. All right? Now you're going to spend this amount on shoes once, and you're going to spend this amount every game. And the total amount that you spend is going to be the cost for the games plus the cost of the shoes, all right? And that total has to be $25 or less. So here's our verbal model. We'll phrase it this way, that the shoe cost added with your game cost has to be less than or equal to your budget. And then let's go ahead and fill in the values that we know for each of those things. The shoe cost is going to be a straight up $3.25. And the game cost is going to be $2.75 times the number of games. Now, that means our unknown value is how many games we can play here, and we'll represent that with a variable. Let's just say it's G for games. And we know your budget then is 25. All right, so you see how that works. Now we can also use the strategy that we used back when I was showing you how to work with equations that have decimals in them. We said you could get rid of the decimals altogether if you wanted to, and we can in this case, and it might be a smart idea. If we can figure out something we can multiply everything by that will move the decimal at least 2 places, that will work for us. So let's just say we multiply everything through by 100 because that'll work. We can say that 325 plus 275G is less than or equal to 2500. Now, getting rid of the decimals is not necessary. Just wanted to reinforce something I've taught you before now. All right, we're still going to isolate both sides. So we're going to say 275G. Sorry, we're going to isolate the variable. 275G is going to be less than or equal to 2500 minus 325, which should be 2175. And then we'll divide 2175 by 275, and we will get that the number of games must be less than or equal to about 7.9. Now, you can't bowl a part of a game. I guess technically you could, but the bowling alley is going to shut you down after every complete game, basically, right? Depending on how you choose to pay. So we're going to say that you could bowl 7 games or less. All right, that's solving linear inequalities. Now, I'll have another video about solving compound inequalities to finish up this section next. Thanks for your attention, guys. Work hard. See you later.